Certainly. Here is your text formatted into paragraphs without skipping any content. The European Social Class for Molecule Research at CERN is uncovering subtleties of another molecule, the smasher. Today, something on various events is more noteworthy and twice as critical. It has seen 3 new particles that could be useful to us in figuring out how our universe was envisioned and what its future looks like. Researchers at CERN have lately revealed disclosures that turn how we interpret the universe on its head. Beneath the external layer of their significant tests lies a tremendous spread of particles and powers so peculiar they could be straight far away from potential segments to different perspectives to particles that challenge the very premise of reality. What bewildering, privileged secrets are hidden inside these tests? Could we skip into the universe of CERN and unwind the bits of information that could re-examine our universe? The entrance to new perspectives, a wormhole, could hypothetically show up out of nowhere, and the explanation would be the remarkable evaluations driven at CERN, home of the immense Hadron Collider, LHC. The LHC is the world's most noteworthy and generally solid molecule smasher, found close to Geneva, riding the line between Switzerland and France. There are privileged secrets about this peculiar connection that the world doesn't have some experience with. Insider facts that could change how we view material science and, in fact, the universe. CERN, the European Organization for Nuclear Research, works this gigantic, consistent instrument. It extends in excess of 27 kilometers and sits profound underground. The essential limit of the massive Hadron Collider is to permit physicists to test the appraisals of various speculations of molecule material science. This consolidates the high-profile evaluation of the standard model of particle physics, which helps us with figuring out the fundamental structure blocks of the universe. At its core, the colossal Hadron Collider works by speeding up protons to basically the speed of light before pounding them together. These impacts produce a shower of new particles, which are studied to acquire insights into the laws of nature. It was through such starters that the Higgs boson, often alluded to as the God particle, was seen as in 2012. This exposure affirmed how particles get mass and was an enormous moment in nuclear material science. The tests driven at the colossal Hadron Collider are critical for figuring out qualities that happen under ridiculous circumstances, basically indistinguishable from those not long after the Big Bang. The information aggregated can fill us in more about how the universe began and about the key constituents of matter. This makes the huge Hadron Collider a player in potentially uncovering new parts of reality, points that could seem okay of insider facts encompassing dark matter and the basic powers of nature. Such high-level trial and error at CERN doesn't come without worries. Some theorize about high-energy tests making dark openings or extraordinary matter that could present dangers to Earth. Anyway, CERN guarantees that all security means are met, and laid-out trained professionals closely monitor these appraisals and studies. Hypothetical models attest that any risky conditions are amazingly far-fetched. Through its constant evaluation and revelations, CERN assists us with figuring out the universe better and shows the amazing limit of human advancement and joint effort in chasing after information. The LHC is mankind's current miracle. The epic Hadron Collider at CERN isn't just an unimaginable piece of innovation. It is a wonder of modern science and engineering. Coordinated under the Swiss-French boundary, the enormous collider goes through a burrow 27 kilometers in width and is pretty much as profound as 175 meters underground. This makes it the largest particle collider on the planet and one of the essential instruments in the field of particle material science. The advancement of the gigantic Hadron Collider is intended to deal with appraisals of noteworthy scale. The head ring of the collider, housed in a burrow with a breadth of 3.8 meters, contains 2 interfacing parallel beam pipes. Each line arranges protons in switch bearings, quickly progressing them with a progression of superconducting magnets. These magnets are critical for keeping up with the way of the protons, bending their course at speeds near that of light. Surrounding the beam pipes are layers of cooling systems that keep a temperature colder than space, required to keep the superconducting magnets at their planned working temperature. The size of the huge Hadron Collider is likewise highlighted by its utilization of thousands of magnets, including 1,232 dipole magnets to twist the beams and 392 quadrupole magnets to concentrate them. The biggest and most powerful superconducting magnets utilized are 15 meters long and weigh 35 tons each. showing the gigantic actual scale and innovative desire behind the collider. The essential job of the Colossal Hadron Collider is to analyze the nuts and bolts of the universe by seeing the littlest pieces of matter. By speeding up particles to basically the speed of light and afterward impacting them, the Huge Hadron Collider permits physicists to concentrate on the subsequent particles that are made during these impacts. This cycle helps in testing and expanding our comprehension of the standard model of molecule physical science, which is the ongoing best portrayal of the subatomic world. One of the key goals behind the tremendous Hadron Collider's tests is to uncover the insider facts of the Higgs boson. Its disclosure at CERN in 2012 affirmed hypotheses about how particles gain mass. The tremendous Hadron Collider, moreover, explores other essential particles and powers, hoping to address fundamental questions like the presence of dark matter and the nature of the universe not long after the Big Bang. The tremendous Hadron Collider desires to confirm the presence of new particles that speculative physical science predicts but has not yet observed. These examinations are key for potentially tracking down new physical science beyond the standard model, including supersymmetry and perspectives beyond the ordinary three-dimensional viewpoints. The vision behind the Colossal Hadron Collider isn't just to figure out the universe's design, however, to encourage worldwide joint effort, with huge numbers of specialists from over 100 countries participating. The gigantic Hadron Collider is proof of overall support in the journey for knowledge. Its design and scale empower it to handle the most serious inquiries in material science. Its motivation reaches out beyond straightforward logical interest, expecting to develop how we decipher the universe and inspire global collaboration in science. Through this immense and complex contraption, mankind continues to stretch the limits of what is known and adventures into the quantum domain. But how does the tremendous Hadron Collider truly work? At the core of CERN's research facilities, the tremendous Hadron Collider fills in as a strong amplifying focal point into the quantum domain, permitting researchers to see and study the basic particles that make up everything in the universe. The course of molecule speed increase and crash at the Huge Hadron Collider is a critical technique for testing the underpinnings of material science. Inside the collider, two high-energy molecule beams travel at almost the speed of light before they are made to impact. These beams travel inside tubes kept at ultra-high vacuum, reproducing the states of space. Superconducting electromagnets, chilled to temperatures colder than space, help steer and concentrate the shafts at assigned influence focuses along the passage. These beams impact, crushing particles along with enormous energy. The impacts produce a variety of subatomic particles, some of which are incredibly unstable and exist only for parts of one moment. To recognize and explore the results of these impacts, the Colossal Hadron Collider is outfitted with enormous locators: ATLAS, CMS, ALICE, and LHCb, each intended for explicit kinds of investigation. These indicators capture information about the particles, including their mass, charge, and energy. This data helps physicists test expectations of molecule physical science speculations, including the norm model and research particles and powers that oversee the universe. One of the main disclosures at the tremendous Hadron Collider was the discovery of the Higgs boson in 2012. This molecule, now and again alluded to as the God particle, is huge because it gives proof to the Higgs field, which is liable for giving mass to essential particles. The presence of the Higgs boson was predicted by the Standard Model, and its disclosure was a great accomplishment, affirming long-established hypothetical forecasts. Beyond the Higgs boson, the tremendous Hadron Collider has likewise been instrumental in tracking down a scope of other particles. For example, the collider has given proof to the presence of pentair and affirmed the presence of tetraquarks, particles made out of 4 and 5 quarks, respectively, particles that had never been observed. These revelations extend our comprehension of hadronic matter, which is matter made of quarks bound together by the strong force, the force that holds atomic cores intact. These disclosures exhibit the preeminent force of the Standard Model and furthermore open new roads of investigation in molecule physical science, offering bits of knowledge into the behavior of matter under outrageous circumstances like those soon after the Big Bang. Theoretical dangers, for example, strangelets or smaller than expected black holes, have been subjects of public interest and logical examination. Strangelets are a speculative type of issue that is more stable than standard matter. The hypothesis proposes that strangelets could change over any matter they come into contact with into strange matter. The trepidation surrounding this hypothesis is that, assuming strangelets were delivered during molecule impacts at the Colossal Hadron Collider, they may trigger a devastating chain reaction, changing overall matter on Earth into strange matter. However, broad examination and security evaluations led by CERN and the worldwide academic community have tended to these worries. Studies have shown that regardless of whether strangelets did exist and were created at the Colossal Hadron Collider, they would most likely be exceptionally unstable and decay too rapidly to cause any change of Earth's matter. Moreover, tremendous cosmic rays, high-energy particles from space, constantly hit the Earth with energy levels far higher than those created by the Colossal Hadron Collider without creating any strangelets. This ordinary appraisal suggests that strangelets are not a tenable danger. The worry that the huge Hadron Collider could create small black holes comes from hypotheses about extra aspects in physical science. From certain perspectives, hypothetical models suggest that high-energy crashes inside the LHC could create small black holes that would vanish in a split second because of a cycle called Hawking radiation, named after physicist Stephen Hawking. Researchers agree that if small black holes were ever created at the LHC, they would represent no risk. First, any such black holes would be little and short-lived, evaporating before they could interact with surrounding matter. Second, the energies associated with LHC impacts, while enormous by human standards, are still far lower than the enormous cosmic ray crashes that happen naturally. Since no hazardous small-scale black holes have been seen from galactic ray interactions, it is incredibly improbable that the LHC would create any risky results. CERN, alongside free sheets, conducts cautious security audits to guarantee that the trials conducted at the LHC represent no danger to mankind or the planet. These surveys incorporate hypothetical examinations, test information, and well-being conventions to address any possible dangers, while the LHC's tests continue to push the limits of how we interpret material science. They are conducted with a serious level of obligation and logical oversight, ensuring that mankind can benefit from notable disclosures without confronting pointless dangers. Theoretical gambles frequently sound more like science fiction than conceivable logical results. The logical agreement, based on broad examination and normal enormous occasions, is that the examinations at the Colossal Hadron Collider are protected and the potential dangers are negligible. One of the most fascinating and uncommon examinations proposed at CERN is the look for magnetic monopoles. A magnetic monopole is a theoretical molecule that is a magnet with only one magnetic pole, either a north pole or a south pole. In contrast, conventional magnets normally have both north and south poles. The presence of magnetic monopoles was anticipated by physicist Paul Dirac in 1931, who showed that their reality would make sense of why electric charge is quantized, meaning it comes in discrete sums. In spite of their hypothetical significance, magnetic monopoles have never been seen at the Large Hadron Collider. Specialists have been looking for proof of these subtle particles. If magnetic monopoles were ever recognized, they would alter our comprehension of magnetic fields and could lead to significant forward leaps in innovation, including the improvement of new kinds of energy stockpiling and transmission. Besides, the disclosure of magnetic monopoles would provide exploratory proof for grand unified theories and string theories, which endeavor to make sense of all major powers of nature within a solitary system. While the quest for magnetic monopoles may seem tricky, it exemplifies the soul of examination and interest that drives logical request at CERN. The journey for such intriguing and potentially groundbreaking particles mirrors the association's responsibility to exploring the obscure and extending the boundaries of human knowledge. Another astounding analysis at the gigantic Hadron Collider involves contemplating the conceivable presence of particles that could travel quicker than the speed of light. As indicated by Einstein's hypothesis of relativity, the speed of light is the extreme speed limit in the universe. However, a few hypothetical models propose that particles called tachyons could exist, which would continuously move quicker than light. Identifying tachyons would generally challenge our comprehension of spacetime and causality. While most physicists still have some doubts about the presence of tachyons, the pursuit for such particles at the gigantic Hadron Collider shows the office's receptiveness to exploring even the most speculative parts of hypothetical physical science. The huge Hadron Collider likewise empowers researchers to direct trials that reproduce states of the early universe, presently after the Big Bang. These high-energy impacts create a condition of matter known as quark-gluon plasma, which existed just minutes after the Big Bang. By concentrating on this plasma, physicists desire to better figure out how the universe developed from its underlying high-energy state into the complex and coordinated universe we notice today. In summary, these various trials at CERN, from looking for magnetic monopoles to making quark-gluon plasma, highlight the expansiveness and aspiration of logical examination conducted at the Huge Hadron Collider. They exhibit how CERN is pushing the limits of what we know about the universe and investigating new areas of material science that were once remembered to be simply speculative. The Huge Hadron Collider's definitive objective is to push the outskirts of human knowledge, entangling the privileged insights of the universe by crushing particles at phenomenal energies. It permits researchers to investigate the major nature of matter and the powers overseeing the universe. This incredible journey for understanding mirrors mankind's characteristic curiosity and want to explore. The disclosures made at the gigantic Hadron Collider have wide ramifications for our comprehension of the universe. By testing the littlest building blocks of matter and the key powers at play, these examinations improve our appreciation of the universe's beginnings, advancement, and ultimate destiny. They offer bits of knowledge into the actual texture of reality and help address the absolute most significant inquiries concerning existence. Besides, the innovative progressions and logical forward leaps rising out of tremendous Hadron Collider research have pragmatic applications beyond molecule material science. The improvement of cutting-edge finders, handling frameworks, and information examination procedures has contributed to progress in various fields, including medication, material science, and information innovation. The Huge Hadron Collider additionally cultivates worldwide cooperation, rousing a new age of researchers and scientists around the world to cooperate, sharing knowledge and expertise. Researchers open the universe's insider secrets. This worldwide joint effort is a demonstration of the power of science to rise above limits and join individuals in the quest for knowledge. The Huge Hadron Collider is a foundation of current material science, empowering groundbreaking disclosures and extending the coffers of what we know about the universe. Its tests reveal the nature of key particles, powers, and the beginnings of matter, offering significant experiences into the insider secrets of existence. Through its mechanical developments and worldwide joint efforts, the gigantic Hadron Collider exemplifies the soul of logical request and the huge capability of human interest. As we keep on investigating the universe through the Huge Hadron Collider, we move nearer to responding to the absolute most basic inquiries concerning our universe and our place within it.